Looking at section 2.3, part 2, we are going to start with an example of finding zeros and their multiplicities. To do a little review of the last piece we looked at yesterday, when we talked about our multiplicities and our x-intercepts, we said if r is a zero of an even multiplicity, meaning we had 2, 4, 6, 8 of them, etc., then the graph touches the x-axis and turns around at that value. They used r. It says if r is a zero of odd multiplicity, meaning you had 1, 3, 5, 7, 9, etc., then the graph crosses the x-axis at r at that point. It says regardless of whether the multiplicity of a zero is even or odd, the graph tends to flatten out near zeros with multiplicities greater than 1. So if we were to look at an example, it says to find the zeros and their multiplicities. So find the zeros of, we have f of x is equal to negative 4 times the quantity x plus a half squared times an x minus 5 to the third, and give the multiplicities of each zero. So state whether the graph crosses the x-axis or touches the x-axis and turns around at each zero. So it says we find the zeros of f by setting f of x equal to 0. So if I were to, in place of f of x, call that 0, we're looking at 0 is equal to negative 4 times, we have that x plus 1/2 squared times an x minus 5 to the third. Now, if we go about solving this, we're solving to get x all by itself. The first thing we would technically want to get rid of is that negative 4, which means we would divide the whole thing by negative 4 to both sides, and the negative 4 still ends up giving that a 0. So it's almost like that negative 4 in a sense cancels out. Or if you are going about doing that zero product property, technically you would say that 0 is equal to negative 4, and you would say each of these pieces are equal to the 0 as well. Well, 0 equals negative 4 is going to give us a no solution, so technically we don't have to worry too much about that. So I'm just going to take this x plus 1/2 to the second power and set that equal to 0. So 0 is equal to the x plus 1/2 to the second power, and 0 is equal to this x minus 5 to the third power. Now we have to find the zeros and we have to find the multiplicities. So let's start by looking at that power. So if I were to look at the second power, is that even or odd multiplicity? Well, a 2 is going to be an even multiplicity, which means it's going to do what? It means it's going to touch the x-axis. If I have a power of 3, I have 3 of these things, which means we have that odd multiplicity. And if it's odd, that means it's going to do what? That means it's going to cross the x-axis. So once we take care of those powers of understanding what those are, then we could just go about solving, well, 0 is equal to what? This is just going to be a 0 is equal to x plus 1/2, which means if we solve to get x by itself, x is going to equal a negative 1/2. So that means our graph is going to touch the x-axis at a negative 1/2. If we solve our other piece, we have 0 is equal to an x minus 5, which means that x is going to equal a positive 5. So at an x-intercept of 5, it's going to cross the x-axis. Because technically, to undo a second power, you would take the square root of 0. That's still 0. To undo the third power, you'd take the third root of 0, which is still 0, which is why we don't have to worry about those powers when we're solving it down for those 0 values. So if we were to continue on with this, we are going to, again, looking at that function, we were able to find our zeros. So the first one we had was a 0 at a negative 1/2. So x is a negative 1/2. That was multiplicity of power of 2. We have that multiplicity of 2. And then we ended up with an x was equal to 5. And that had a multiplicity of third power. That's where this 3 is. So the graph will, we already said, it's going to touch the x-axis at x equals negative 1/2, and the graph is going to cross the x-axis at an x is equal to 5. So now we need to kind of figure out, well, what's happening with this? We need to go back to looking at our powers. If I have a second power and a third power, all together we have a fifth degree function. Fifth degree function, that means that we have either it's going up and it's going down, or it's starting from the down and it's going to the up. So then we go back and we look at our leading coefficient, that -4. What does that mean? That means that we are going to end up with, we're not going to start from the bottom and go to the top. We are going to start from the top and go to the bottom. If you don't know what I'm talking about, go back and look at the very beginning of the lesson for section 2.3. So that means when we're looking at this x-intercept of -1/2, and we have an x-intercept of +5, we can identify that going off to that left-hand side, this is going to rise to the left-hand side, and it's going to fall to the right-hand side. Now, if it's going to touch the x-axis at -1/2, that means that this is going to come down and it's going to touch at -1/2, and it's going to turn back around and go back up. And then on the other side, we said it's going to cross at that 5. So that means that this graph has to turn around somewhere to come back down and go through that 5. And again, these are all just rough sketches. These are not exact answers. They're just to get the general picture of what's going on with that graph, right? It's going to come down. It's going to touch at that -1/2. It's going to go back up. It's going to turn back around, and then it's going to cross at that +5. So next we're going to talk about what's called the intermediate value theorem. So it says let f be a polynomial function with real coefficients. It says if f of a, the value of the function at value a, and f of b, the value of the function at b, have opposite signs, meaning one of them is positive and one of them is negative, then there is at least one value c between a and b for which f of c is equal to 0. It says equivalently, the equation f of x is equal to 0 has at least one real root between a and b. A whole bunch of words and a whole bunch of what in the world does that mean? So what happens is if I were to take a graph and I were to look at, I'm just going to pick an a value here and a b value here. They're saying if the value of a and the value of f of a and the value of f of b are opposite signs, meaning something happens that I have, that was really ugly. I have a value of a, comma, the value of the function at a, and I have b and the value of the function at b. If this here and this here have opposite signs, f of a in my case would be a negative value. F of b would end up being a positive value. They're saying if one of them is positive and one of them is negative, then somewhere in between here is going to be a c value that has f of x is equal to 0. The f of c is equal to 0. You would have a point at which it's going to end up having a real solution between that a value and that b value. The next part talks about turning points of polynomial functions. It says, in general, if f is a polynomial function of degree n, the graph of f has at most n minus 1 turning points. Now, if you think about this, if I had, I'm just going to go back to the basics. Y is equal to x squared. Y equals x squared means that we have a parabola. How many turning points does it have? It has one turning point. That is n minus 1. 2 minus 1 is equal to 1. The most number of turning points that's going to have is 1. If I were to look at y is equal to x to the third power. Now, regular y equals x to the third would just end up looking like a graph like this. However, if you get fancy with it, it could do something like this. So if I have 3, the greatest number of turning points it could have would be 3 minus 1, which would give us 2 turning points. Here's one turning point, here's a second turning point. If I were to even go back to an example that we did in the previous lesson, we had our f of x was equal to, we had x to the fourth minus 4x squared. And if you remember, that kind of looked like this funny looking W graph. Well, how many turning points does that have? That has 1, 2, 3. Well, if I had fourth power, 4 minus 1, the most number of turning points I could see is going to be 3. So kind of two concepts to look at here. So the example says, using the intermediate value theorem, it says show that the polynomial function f of x equals 3x to the third minus 10x plus 9 has a real zero between -3 and -2. So it says we're going to evaluate f, the function, at -3 and -2. If f of -3 and f of -2 have opposite signs, again, that means that we have one positive, one negative answer, then there is at least one real zero between -3 and -2. At least means that there could be more depending on what the highest degree of the function is in terms of those turning points. But we're looking for at least one. So what we're going to do is we're going to plug in -3 and -2 to our function, find out what those answers are. If they're opposite signs, then we can say, yes, there's going to be one real solution in between there. So if we take a -3, we'd have a 3 times a -3 to the third minus 10 times a -3 plus 9. So let's see if we simplify that down. -3 to the third power, that's a -27. So 3 times a -27, that is a -81. Minus and a negative, that's going to be plus 30. And then we're going to add 9. So -81 plus 30 and then plus 9, we're going to end up with a -42. If we evaluate f of -2. Erase that so I have a little bit more room. If I were to evaluate my f of -2, we're going to take 3 times the -2 to the third power minus 10 times -2 plus 9. So -2 to the third power, that's a -8. 3 times the -8, so we have -24. We are going to add 20, and then we are going to add 9, and that's going to end up giving us a positive 5. Now, looking at these two values here, one of them is negative and one of them is positive. We have a negative number. We have a positive number. What does that mean? There is at least one real solution between them. One real solution, one real root. Forget what they were asking, a real zero. All right, all those interchangeable terms. So continuing on with that, f of -3, we said we ended up with a -42. And f of -2, we ended up with 5. So it says that the sign change shows that the polynomial function has a real zero between -3 and -2. When we were at -3, we had -42. That's where this kind of ordered pair would have ended up being that point. And when we were at -2, we had an answer of 5. At -2, we were at 5. Here is our one real solution. There's that value. That shows us that it's going to cross that x-axis somewhere at -2-ish.